Welcome back, everyone. Today we're diving into another two important aspects of networking: protocols and networking models. Understanding networking protocols is like knowing the language of the internet. It's what allows devices to communicate effectively. Think of protocols as road signs or guidelines that dictate how data should travel from one point to another. Networking models, on the other hand, provide a structured framework for understanding and implementing these protocols. They offer a blueprint that organizes the tasks and functions of networking into layers, each handling specific responsibilities. Two of the most widely used models are OSI and TCP/IP. The Open Systems Interconnection, OSI for short, model divides the networking process into 7 layers, and more of a theoretical model, while TCP/IP, which stands for Transmission Control Protocol and Internet Protocol model, is a practical model that our computers use and how networking actually happens. These models ensure that protocols work together across different hardware and software platforms, creating a network architecture that makes up modern communication and connectivity. Understanding both protocols and networking models is essential for anyone looking to grasp the complexities and efficiencies of today's interconnected world, and will aid you in understanding of how to better protect them. Let's break down some of the key protocols that form the backbone of modern network communications. First, we'll start with TCP/IP, which again stands for Transmission Control Protocol and Internet Protocol, and it has the exact same name as the networking model that we've just discussed. TCP is the foundation of the internet. It ensures that data packets are delivered reliably from one endpoint to another over the network. TCP handles the assembly and disassembly of packets, ensuring data integrity, while IP handles the addressing and routing of packets across the network. Unlike TCP, UDP, which stands for User Datagram Protocol, is a connectionless protocol that prioritizes speed over reliability. It is commonly used for real-time applications such as streaming media, online gaming, and voice over IP, which is what a lot of office phones use these days. UDP sends data packets without establishing connection or verifying receipt, making it faster but less reliable than TCP. Next up, we have HTTP, which stands for Hypertext Transfer Protocol. HTTP is the protocol used for transferring hypertext documents on the World Wide Web. It defines how web browsers and servers communicate, allowing users to access and interact with web pages, images, videos, and other web resources. HTTPS, then, is a secure version of HTTP, encrypted using SSL, or in modern times actually TLS protocols. It ensures that data transfer between web browser and the web server remains confidential and secure, making it ideal for online transactions, sensitive information exchange, and secure browsing. Another common protocol is FTP, which stands for File Transfer Protocol. It's used for transferring files between a client and a server on a network, as the name suggests. It provides a simple and reliable method for uploading, downloading, and managing files remotely. FTP operates on a client-server model, where clients initiate file transfer to or from a designated FTP server. Second last one we will mention is Simple Mail Transfer Protocol. SMTP is a standard protocol used for sending and receiving email messages over the internet. It defines how email clients and mail servers communicate to deliver emails from sender to recipient. SMTP ensures that emails are routed and delivered efficiently across different mail servers. Lastly, let's discuss DNS, Domain Name System. DNS is a hierarchical naming system that translates domain names, for example www.google.com, into IP addresses that computers can understand. It enables users to access websites and other internet resources using human-readable domain names instead of numeric IP addresses. Imagine having to remember all of your friends' phone numbers without being able to search them by name on your phone. Well, this is a similar concept. Before we wrap up talking about protocols, I want to mention that there is another difference between the TCP and UDP and the rest of the protocols we have mentioned. TCP and UDP are lower-level protocols, while the rest of the ones that we went over are higher-level protocols. Higher-level protocols such as HTTP, HTTPS, FTP, SMTP, and DNS rely on TCP for reliable data transmission, ensuring that information is delivered accurately and securely. Meanwhile, as I've mentioned, UDP provides a lightweight and efficient communication mechanism for protocols like DNS, enabling quick and responsive interaction between network devices. As we dive deeper into the intricacies of network communication, it's essential to explore the OSI and TCP/IP models. Let's take a look at this diagram. The OSI model provides a structured framework for understanding how data flows across networks, breaking down the process into 7 distinct layers. Each layer plays a unique role in facilitating communication between devices, from the physical transmission of data to the application-level interactions. By comprehending the functions of each OSI layer, we gain valuable insights into how networks operate and how to troubleshoot issues effectively. Let's discuss the layers of the OSI model and discover their significance in contributing to the different types of transmission of data across the networks. From the physical layer, where data is transmitted in the form of electrical signals, to the application layer, where user interactions occur. The OSI model provides a comprehensive framework for understanding network communication. By dissecting each layer's functions and interactions, we gain deeper appreciation for the complexity and robustness of modern network systems. Let's briefly talk about each layer. The physical layer is the lowest layer of the OSI model and deals with physical transmission of data over the network medium. It includes specifications for cables, connectors, network interface cards, and other hardware components. An example of the physical layer in action is the Ethernet cable connecting your computer to your router. Well, I guess these days it's more common to use Wi-Fi to connect to your router. However, that's still an example of the physical layer. The data link layer is responsible for establishing and maintaining a reliable link between nodes over a physical connection. It handles error detection and correction, as well as data framing. An example of the data link layer is the MAC address of your computer's network interface card, NIC for short. This address uniquely identifies your device on the local network. The network layer is responsible for logical addressing and routing of data packets between different networks. It determines the best path for data transmission and handles logical addressing such as IP addressing. An example of the network layer is the IP address assigned to your device, which we've discussed earlier. Just as GPS coordinates guide you to your destination, IP address directs data packets to their intended recipients across the internet. Other protocols associated to this layer are ARP, IGMP, and ICMP. The transport layer ensures reliable and efficient data transfer between end systems. It handles segmentation and reassembly of data, as well as flow control and error recovery mechanisms. This is where our protocol discussion began. A real-life example of UDP is video streaming. When you watch a live video stream or video on demand service like YouTube, UDP is often used to deliver the video data from the server to your device. On the other hand, when you compose and send an email, using a client like Gmail or Outlook, TCP ensures that your message is reliably delivered from your device to the email server and then to the recipient's email server. Next, we have the session layer, which establishes, maintains, and terminates connections between applications running on different devices. It manages sessions, allowing for synchronization and checkpointing of data exchanges. A good example of this would be when you log in to a remote server using a protocol like SSH, which stands for Secure Shell. The session layer manages the establishment of the SSH session between your local computer and the remote server. It ensures that the communication between your terminal and the SSH server remains intact during the session. It also handles the orderly termination of the session once you log out or close the connection. The session layer in this case ensures that the communication is reliable, handles any errors that may occur during the session, and maintains the integrity and synchronization of the data exchanged between the two endpoints. Layer 6, or the presentation layer, is responsible for data translation, encryption, and compression to ensure compatibility between different systems. It handles the formatting and presentation of data for the application layer. When you watch a movie on a streaming platform like Netflix or YouTube, the presentation layer is responsible for formatting the digital video data received from the server into a viewable format on your device's screen. This layer ensures that the video is displayed correctly with the appropriate resolution, aspect ratio, and color depth, so you can enjoy high-quality viewing experience. Additionally, the presentation layer may handle tasks like encryption and compression to secure the video data during transmission and optimize bandwidth usage for smoother streaming. Some of the protocols of this layer are Apple Filing Protocol, Network Core Protocol, External Data Representation, and SSL and TLS for encryption. Finally, last but not least, we have the application layer, which is the topmost layer of the OSI model and provides network services directly to end users and applications. It includes protocols such as HTTP, FTP, SMTP, and DNS, which enable communication and data exchange between applications. The application layer is perhaps the most relatable layer for everyday users. The user-friendly interface of various software applications we use on our devices is exactly that. For example, consider your web browser such as Google Chrome or Mozilla Firefox. When you open your browser and visit a website, you're interacting with the application layer. The application layer enables you to access and interact with a variety of online services, including email, social media, search engines such as Google, online shopping like Amazon, and more. Each website or service you access through your browser operates as the application layer, providing you with the familiar interface and functionality you rely on to navigate the digital world. Now that we've explored the OSI model and gained insights into its layers and functionalities, let's shift our focus to another important model in networking, the TCP/IP model. While the OSI model provides a conceptual framework for understanding network communication, the TCP/IP model offers a practical approach tailored to the Internet's architecture. Let's examine TCP/IP model and briefly compare its structure and layers to those of the OSI model. Before going into the specifics of the TCP/IP model, it's worth mentioning that while the OSI model consists of 7 distinct layers, the TCP/IP model is made up of 4 layers. This streamlined structure aligns more closely with the protocols and architecture of the Internet. making it highly relevant in today's digital landscape. As we briefly explore the TCP/IP model, let's discuss its layers and functionalities and how it facilitates network communication. In the TCP/IP model, the network interface layer, also known as the link layer, governs the physical transmission of data across the network medium. It combines both the physical and data link layers of the OSI model. Network interface layer encompasses protocols and standards relating to physical and wireless connections, like Ethernet and Wi-Fi. This layer ensures data is correctly formatted for transmission and manages connections between devices on the same network segment. The Internet layer is responsible for addressing and routing data packets between various networks. It utilizes Internet Protocol IP to assign unique addresses to devices and determine the most efficient path for data transmission. Additionally, protocols like ICMP operate here to resolve connectivity issues. Sitting on top of the Internet layer is the transport layer, which ensures reliable data delivery between nodes. It segments data into smaller packets and reassembles them at the destination, making end-to-end communication. As we've discussed, protocols like TCP, Transmission Control Protocol, provide reliable connection-oriented communication, while UDP, User Datagram Protocol, offers faster, connectionless transmission. I know I'm repeating myself, but I just want to solidify these concepts. At the highest level, we have the application layer, which combines session, presentation, and application layers of the OSI model. It facilitates communication between user applications and the network. It includes protocols tailored for specific applications, such as HTTP for web browsing, SMTP for email, FTP for file transfer, and DNS for domain name resolution. Serving as the interface between users and the network, this layer enables access to network services and resources. Together, these layers collaborate to enable communication and data exchange across networks, forming a cornerstone of modern internet connectivity and services. Understanding each layer's functionality is crucial for troubleshooting network issues, optimizing performance, and designing efficient network architectures. To conclude, in today's discussion of networking, we went over protocols and models, essential for effective communication across networks. Understanding network protocols is crucial for ensuring data transmission, as they dictate how data flows and are regulated by ports, which we're going to talk about in the next lesson. We explored common networking protocols like TCP, UDP, HTTP, HTTPS, FTP, SMTP, and DNS, understanding their roles in shaping data movement. We've distinguished TCP's reliability from UDP's speed, showcasing their real-world applications. We then went over two different internet models, OSI and TCP, along with their layers, each contributing to network communication. From physical transmission to user interactions, we illustrated each layer's functions. Remember, OSI is a theoretical model, while TCP/IP is a practical one. OSI has 7 layers and TCP/IP has 4 layers. Understanding networking protocols and models is essential for ethical hacking, as it enables professionals to identify vulnerabilities, develop exploitation techniques, conduct penetration testing, and enhance network defense strategies. By comprehending how network operates and how protocols function, ethical hackers can effectively assess security risks, simulate cyber attacks, and strengthen defenses to safeguard against potential threats. After covering the basics of networking protocols and models, viewers are encouraged to further their understanding through practical exercises and additional resources available online. Engaging in hands-on activities and exploring relevant materials will help solidify your knowledge and skills in networking and cybersecurity. In the upcoming video, we will focus on ports, which play a role in directing data traffic within the networks. While protocols define the rules and standards for communication between devices, ports provide a way to organize and manage this communication. See you there. Thank you for joining us in today's lesson. We hope you found valuable insights that will enhance your understanding of proactive cybersecurity measures. Your attention and participation are greatly appreciated. To stay updated on the latest content and insights in ethical hacking and cybersecurity, don't forget to like, share, and subscribe to our channel. Your support helps us continue providing informative content to our community.